Right now, beneath your feet, an entire world exists in constant, gentle motion. While you sit here, reading these words, feeling perfectly still and stable, the earth beneath you is alive with processes so vast and so slow that they unfold across timescales our minds can barely comprehend. Deep inside our planet, in chambers of rock and metal that no human will ever see, a quiet symphony of geological forces continues its ancient rhythm, just as it has for over 4 billion years. Tonight, we're going to take a journey together, descending slowly through the layers of our planet, discovering what's happening right now in the deepest places on Earth. We'll move gently through each layer, understanding how heat flows upward like a patient breath, how metals swirl in patterns that create the invisible shield protecting all life above, and how solid rock moves like honey over millions of years, reshaping continents grain by grain. This isn't a story of violence or catastrophe. It's a story of continuity, of processes so steady and reliable that they've maintained the conditions for life for billions of years. As we explore together, let the slow, eternal rhythms of the deep earth remind you that beneath all the chaos of daily life, something vast and stable continues its work, unhurried and unworried, following the same patterns it has followed since before the first sunrise. So settle in comfortably, and let's begin our descent into the quiet heart of the world. The journey starts just beneath the surface, where the familiar world of soil and rock gives way to something far more mysterious and wonderful. If you were to drill straight down through the ground beneath you, the first few meters would reveal the familiar world of soil, roots, and weathered rock. But continue deeper, past the reach of any shovel or well, and you would enter the Earth's crust, a thin shell of solid rock that wraps around our planet like the skin of an apple. This crust, where all human life unfolds, extends down only 30 to 50 kilometers beneath the continents, and just 5 to 10 kilometers beneath the ocean floors. The crust feels permanent to us, but in the context of the whole Earth, it's almost impossibly thin. If our planet were scaled down to the size of a basketball, the crust would be thinner than a coat of paint. Yet within this delicate layer, all the mountains, valleys, oceans, and continents exist, riding on something far more substantial below. Beneath the crust lies the mantle, a layer of rock so vast it contains 84% of the Earth's total volume. The mantle extends from the bottom of the crust all the way down to a depth of 2,900 kilometers, nearly 2,000 miles beneath the surface. To put this in perspective, if you could somehow dig a tunnel through the mantle, the journey would take longer than driving across the entire United States. Right now, as you listen to these words, the mantle is engaged in a process so gradual and so immense that it defies our everyday understanding of motion. The rock of the mantle, heated by the Earth's core and by the slow decay of radioactive elements, is moving. Not quickly, not violently, but with the patient persistence of geological time. Hot rock rises slowly from the deep, while cooler rock sinks downward, creating vast circulation patterns called convection currents. These currents move at roughly the same speed your fingernails grow, just a few centimeters per year. A single convection cycle in the mantle takes between 50 and 200 million years to complete. This means that rock currently rising from the deepest parts of the mantle began its journey upward when the first flowers were blooming on Earth's surface. The rock beneath your feet has been on a journey longer than the entire history of complex life. The temperature in the mantle increases gradually with depth. Near the top, just below the crust, temperatures hover around 1,000 degrees Celsius, hot enough to melt copper. Deeper down, near the boundary with the core, temperatures reach over 4,000 degrees Celsius, approaching the temperature of the sun's surface. Yet despite these intense temperatures, most of the mantle remains solid rock. The enormous pressure at these depths, hundreds of thousands of times greater than atmospheric pressure, keeps the rock from melting. This solid rock behaves in ways that seem impossible on the surface. Under the immense pressure and heat of the deep earth, solid rock can flow like thick honey, deforming and moving over thousands and millions of years. The process is similar to how a glacier flows down a mountain, remaining solid ice while slowly changing shape and flowing downhill. In the mantle, entire mountain ranges of rock rise and fall in slow motion, following currents that have been flowing for hundreds of millions of years. The composition of the mantle tells a story of the Earth's formation. It consists primarily of silicate minerals rich in iron and magnesium, the heavy elements that sank toward the center during the planet's violent birth 4.5 billion years ago. These minerals transform under pressure, taking on new crystal structures as they sink deeper or rise higher in the mantle's circulation. At certain depths, these transformations create boundaries where seismic waves change speed, allowing scientists to map the mantle's structure using earthquakes as their eyes. Recent discoveries have revealed that the mantle is not a simple, uniform layer. Deep within it, scientists have found evidence of ancient oceanic crust that was pushed down into the Earth's interior millions of years ago, now slowly mixing with the surrounding rock. They've discovered vast regions where the rock is slightly different in composition, possibly preserving chemical signatures from the earliest days of the planet. These discoveries suggest that the mantle acts as a kind of geological memory, preserving evidence of processes that occurred billions of years ago. The movement of the mantle drives everything we see on the surface. The slow circulation of rock creates the forces that push continents apart and bring them together. Where hot rock rises toward the surface, it can create volcanic islands like Hawaii. Where cool rock sinks into the deep, it can pull oceanic plates down into deep ocean trenches. The mantle's patient circulation has been reshaping the surface of the Earth for billions of years, building and destroying mountain ranges, opening and closing ocean basins, and slowly wandering the continents across the globe. But the mantle is just the beginning of our journey into the deep Earth. Below it lies something even more remarkable, a region where rock gives way to liquid metal, and where one of the most important processes for life on Earth takes place in complete darkness, under pressures that would instantly crush anything from the surface world. At 2,900 kilometers below the surface, the mantle gives way to something fundamentally different. Here begins the Earth's core, a sphere of metal larger than the planet Mars, hidden beneath thousands of kilometers of rock. The core is divided into two distinct regions, an outer core of liquid iron and nickel, and an inner core where the same metals exist as a solid ball under unimaginable pressure. The outer core extends from the base of the mantle down to about 5,200 kilometers below the surface. Unlike the solid rock of the mantle above, the outer core is completely liquid, a sea of molten iron and nickel at temperatures between 4,000 and 6,000 degrees Celsius. This liquid metal moves in complex patterns, driven by heat escaping from the inner core and the rotation of the Earth itself. Right now, as you rest quietly on the surface, this liquid metal is flowing in currents that span thousands of kilometers. These flows are not random or chaotic. They follow patterns influenced by the Earth's rotation, the cooling of the core, and the crystallization of iron onto the inner core boundary. The liquid moves slowly by human standards, perhaps a few kilometers per year, but this represents enormous streams of molten metal carrying vast amounts of heat and electrical current. These flowing streams of liquid metal create something extraordinary: Earth's magnetic field. As the electrically conductive liquid iron moves through the existing magnetic field, it generates electric currents, which in turn create new magnetic fields. This process, called the geodynamo, has been operating for billions of years, creating and maintaining the magnetic field that surrounds our planet and extends far into space. The magnetic field generated by the core is not just an interesting phenomenon, it's essential for life on Earth. This invisible shield deflects most of the solar wind, a stream of charged particles flowing constantly from the sun. Without the magnetic field, these particles would strip away our atmosphere over geological time, leaving Earth a barren, airless world like Mars. The gentle motion of liquid metal thousands of kilometers beneath your feet is directly responsible for the existence of the atmosphere you're breathing right now. The inner core, beginning at about 5,200 kilometers depth and extending to the very center of the Earth, exists under conditions almost impossible to imagine. Here, the pressure is over 3 million times greater than atmospheric pressure at sea level. Under this enormous pressure, iron and nickel are squeezed into a solid crystal despite temperatures that exceed 5,000 degrees Celsius, hotter than the surface of the sun. This solid inner core is not static. It's growing slowly as the Earth continues to cool, with liquid iron from the outer core crystallizing onto its surface at a rate of about 1 millimeter per year. This process has been continuing for over 1 billion years, and it releases heat that helps drive the convection in the outer core above. The crystallization of iron onto the inner core also releases lighter elements that rise up through the outer core, contributing to the complex patterns of flow that generate the magnetic field. Recent discoveries have revealed that the inner core is even more complex than scientists once thought. In 2024, researchers discovered a donut-shaped region within the outer core, located near the boundary with the mantle and parallel to the Earth's equator. This structure appears to affect how seismic waves travel through the region, suggesting that the flow patterns in the outer core are more intricate than previously understood. The inner core itself appears to have its own internal structure. Scientists have found evidence that it may consist of different layers, possibly formed at different times in Earth's history as the core slowly cooled and crystallized. Some research suggests that the very center of the Earth may have properties different from the surrounding inner core, though this remains an active area of scientific investigation. The heat generated by the core is not just from the crystallization of iron. Deep within the Earth, radioactive elements like uranium, thorium, and potassium continue to decay, just as they have for billions of years. This radioactive decay generates heat continuously, contributing to the thermal energy that drives convection in both the core and the mantle. The decay of these elements provides a steady source of energy that has kept the Earth's interior hot and active throughout its history. The boundary between the core and mantle is one of the most dramatic transitions on our planet. Here, liquid iron meets solid rock, and the contrast in density is greater than the difference between water and air at Earth's surface. This boundary is not smooth or simple. Scientists have discovered vast regions where the rock just above the core mantle boundary has unusual properties, possibly representing ancient material from the early Earth that has been preserved for billions of years. These mysterious structures, some as large as continents, may influence the flow patterns in both the core and the mantle. They could affect how heat flows from the core into the mantle above, influencing the location of volcanic hotspots and the patterns of convection that drive plate tectonics. The study of these structures is helping scientists understand how the deep Earth has evolved over geological time and how different layers of the planet interact with each other. As we've journeyed downward through the layers of the Earth, we've discovered a world of motion and energy that operates on scales almost impossible to comprehend. The gentle circulation of rock in the mantle, the flowing streams of liquid metal in the outer core, the slow growth of the inner core. All of these processes continue right now, beneath our feet, following patterns established billions of years ago and continuing into a future so distant, it encompasses millions of human lifetimes. The interaction between the core and mantle creates phenomena that ripple upward through thousands of kilometers of rock, eventually reaching the surface world where we live. At the core mantle boundary, 2,900 kilometers below, Temperatures and pressures create conditions unlike anywhere else in our solar system. Here, the liquid iron of the outer core meets the solid rock of the mantle's deepest layer, and this meeting generates some of the most important processes affecting our planet's surface. Scientists have discovered that this boundary region is far from uniform. Vast structures, some larger than entire continents, rest along this interface between metal and rock. These structures, called large low-shear velocity provinces, are regions where seismic waves slow dramatically as they pass through. One sits beneath Africa, another beneath the Pacific Ocean, each representing billions of years of geological evolution frozen in the deep Earth's memory. These massive formations appear to be remnants of ancient processes, possibly dating back over 4 billion years to when the entire Earth was molten. As the planet slowly cooled and differentiated, with heavy metals sinking toward the center and lighter materials rising toward the surface, some of this primordial material may have been preserved at the core mantle boundary. These structures influence how heat flows from the core into the mantle, affecting the patterns of convection that ultimately drive the movement of continents on the surface. The heat flowing upward from the core varies across the planet's surface. In some regions, particularly beneath the large low-shear velocity provinces, heat flow appears to be reduced, while in other areas, heat escapes more readily. This uneven heating creates variations in the mantle's convection patterns, leading to the formation of mantle plumes, columns of unusually hot rock that rise slowly from the core mantle boundary toward the surface. These mantle plumes move upward through the solid rock of the mantle, like enormous slow-motion balloons of heat. The journey takes millions of years, with the hot rock gradually rising through the surrounding cooler material. When these plumes finally reach the base of the lithosphere, the rigid outer shell of the Earth, they can create volcanic hotspots that persist for tens of millions of years. The Hawaiian island chain provides a beautiful example of this process in action. As the Pacific Plate moves slowly northwest over a stationary mantle plume, the rising hot rock creates volcanoes that build islands above sea level. Over time, as the plate continues its patient movement, each island moves away from the plume source and becomes extinct, while new volcanoes form in its place. This process has been creating the Hawaiian Emperor Seamount chain for over 70 million years, leaving a trail of volcanic islands and underwater mountains that stretches across thousands of kilometers of ocean floor. Similar processes occur beneath other parts of the world. Iceland sits atop a mantle plume that has been active for at least 60 million years, creating the volcanic island and contributing to the spreading of the Atlantic Ocean. The Yellowstone region of North America lies above a plume that has left a track of ancient volcanic calderas, as the North American plate has moved slowly southwest over the hotspot. These deep earth processes operate according to rhythms that span geological time. The mantle plumes that create surface volcanism today began their journey upward when the continents were in completely different positions, when different species dominated life on Earth, when the climate and ocean chemistry were vastly different from today. The rock currently emerging at mid-ocean ridges was last at the surface hundreds of millions of years ago, when the first animals were exploring the land. The circulation of material between the surface and the deep earth creates a kind of planetary recycling system that has operated for billions of years. Ocean floor created at mid-ocean ridges eventually travels across ocean basins and descends back into the mantle at subduction zones, carrying with it water, sediments, and sometimes even pieces of continents. This subducted material sinks slowly through the mantle, eventually reaching the core mantle boundary, where it may remain for hundreds of millions of years before beginning the long journey back toward the surface. This recycling process affects the chemical composition of volcanic eruptions around the world. Volcanoes above subduction zones often produce lavas with chemical signatures that reveal the presence of recycled ocean floor, sometimes including materials that were originally formed billions of years ago. The Earth's interior acts as a vast reservoir, storing and slowly mixing materials from different ages and environments, creating the complex chemical patterns we observe in modern volcanic rocks. The movement of material through the mantle also influences the planet's climate over geological timescales. When carbon-rich sediments are subducted into the mantle, they can eventually return to the surface through volcanic eruptions, affecting atmospheric carbon dioxide levels. The rate of seafloor spreading and subduction influences how quickly carbon is recycled between the solid Earth and the atmosphere, helping to regulate global temperatures over millions of years. The magnetic field generated by the outer core provides a window into the deep Earth's behavior that scientists can observe and measure. The strength and direction of the magnetic field change slowly over time as the flow patterns in the liquid outer core evolve. These changes are recorded in volcanic rocks as they cool and solidify, preserving a record of the magnetic field's behavior over millions of years. This paleomagnetic record reveals that the Earth's magnetic field has undergone dramatic changes throughout geological history. The field has reversed its polarity hundreds of times, with magnetic north and south switching places over periods of thousands to millions of years. These reversals appear to be related to changes in the convection patterns within the outer core, possibly triggered by the slow evolution of temperature and composition at the core-mantle boundary. Currently, the magnetic field is weakening in some regions and strengthening in others, suggesting that another reversal might occur within the next few thousand years. However, even during magnetic reversals, the field doesn't disappear entirely. It becomes more complex, with multiple magnetic poles and reduced overall strength, but it continues to provide some protection from solar radiation. The study of the magnetic field also reveals details about the structure of the outer core that would be impossible to determine through other means. Variations in the magnetic field measured at the Earth's surface reflect changes in the flow of liquid iron thousands of kilometers below. By tracking these variations over time, scientists can map the circulation patterns in the outer core and understand how they change in response to the slow cooling and evolution of the Earth's interior. Recent discoveries have revealed that the outer core contains structures and flow patterns that were not anticipated by earlier models. The donut-shaped region discovered in 2024 near the top of the outer core suggests that the boundary between the liquid core and solid mantle influences the flow of liquid metal in complex ways. This structure appears to be related to the way the liquid iron interacts with the solid rock above, creating circulation patterns that differ from the simple convection cells once thought to dominate the outer core. The inner core, that solid sphere of iron and nickel at the very center of the Earth, continues to grow as the planet slowly cools. Each year, approximately 1 millimeter of new solid iron crystallizes onto the surface of the inner core as heat escapes upward through the overlying layers. This may seem like an insignificant amount, but over geological time, this process has created a solid metallic sphere larger than the Moon, suspended in an ocean of liquid metal under pressures that exceed 3 million atmospheres. The crystallization of iron onto the inner core releases latent heat and expels lighter elements that rise upward through the liquid outer core. These rising plumes of light material help drive the convection that generates the magnetic field, creating a direct connection between the cooling of the planet's center and the magnetic shield that protects life at the surface. The inner core itself has structure and complexity that scientists are only beginning to understand. Seismic waves traveling through the inner core reveal that it has different properties in different directions, suggesting that the iron crystals are aligned in preferred orientations. This alignment may result from the flow of liquid iron in the outer core, which could influence how new iron crystallizes onto the inner core surface. Some evidence suggests that the inner core may have grown in distinct phases throughout Earth's history. The very center of the inner core may have different properties from the outer portions, possibly reflecting changes in the conditions under which it formed. These differences could preserve information about the Earth's thermal evolution over the past billion years, providing clues about how the planet's interior has changed as it slowly loses heat to space. The heat driving all these processes comes from several sources that continue to operate billions of years after the Earth's formation. The planet retains heat from its original accretion, when countless impacts compressed and heated the material that would become our world. Gravitational energy released as heavy materials sank toward the center during planetary differentiation also contributed significant heat that continues to escape today. Radioactive decay provides an ongoing source of internal heat that will continue for billions of years into the future. Uranium, thorium, and potassium atoms scattered throughout the Earth's interior decay at predictable rates, releasing energy that helps maintain the temperature gradients, driving mantle convection and core circulation. This radioactive heating is distributed throughout the planet, but is particularly concentrated in the continental crust and the mantle, where these elements are more abundant than in the iron-rich core. The combination of primordial heat and radioactive decay maintains the Earth as a thermally active planet, distinguishing it from smaller bodies like the Moon and Mars that have largely cooled and become geologically inactive. The balance between heat generation and heat loss determines the vigor of mantle convection, the strength of the magnetic field, and the level of volcanic and tectonic activity at the surface. Scientists study these deep Earth processes through indirect methods, since no human-made instrument can survive the journey to the planet's center. Seismic waves generated by earthquakes provide the primary tool for imaging the Earth's interior. These waves travel through the planet at speeds that depend on the temperature, pressure, and composition of the materials they encounter, allowing scientists to create detailed maps of internal structure. Different types of seismic waves reveal different aspects of the Earth's interior. Compressional waves can travel through both solid and liquid materials, but shear waves can only propagate through solids. The disappearance of shear waves in the outer core provided the first evidence that this region is liquid, while their reappearance after passing through the outer core revealed the existence of the solid inner core. Modern seismic networks around the world continuously monitor earthquake waves as they travel through the planet, gradually building more detailed pictures of internal structure. Advances in computational power allow scientists to model how seismic waves should behave in different hypothetical Earth models, comparing these predictions with observations to refine their understanding of conditions deep below the surface. Laboratory experiments complement seismic studies by recreating the extreme pressures and temperatures found in the Earth's interior. Using diamond anvil cells and other high-pressure devices, scientists can squeeze tiny samples of rock and metal to conditions equivalent to those thousands of kilometers underground, observing how materials behave under these extreme conditions. These experiments reveal how minerals transform under pressure, how their physical properties change with temperature, and how they conduct heat and electricity. The results help interpret seismic observations and provide the physical understanding needed to model how the Earth's interior evolves over time. The deep Earth remains largely mysterious despite these sophisticated investigative techniques. Each new discovery raises additional questions about the complex processes operating in the planet's interior. The recent identification of the donut-shaped structure in the outer core, the discovery of unusual mineral phases at extreme pressures, and the mapping of large-scale structures at the core mantle boundary all point toward a deep Earth that is more complex and dynamic than previously imagined. Future research will continue to reveal new aspects of our planet's hidden interior. Planned seismic experiments will provide higher-resolution images of mantle structure. New laboratory techniques will recreate ever more extreme conditions, helping scientists understand how materials behave under the pressures and temperatures found at the Earth's center. Computational models will become more sophisticated, incorporating the complex physics of heat transfer, fluid flow, and mineral behavior under extreme conditions. As we deepen our understanding of the Earth's interior, we gain greater appreciation for the remarkable stability of the processes that have maintained our planet as a habitable world for billions of years. The slow circulation of the mantle has regulated surface temperatures, by controlling the rate at which carbon is recycled between the solid Earth and the atmosphere. The magnetic field generated by the core has protected the atmosphere from erosion by the solar wind. The gradual cooling of the planet has provided a steady supply of volcanic gases that helped create and maintain the oceans. These processes continue today with the same patient persistence they have shown throughout geological time. The rock beneath your feet is slowly moving, carrying continents across the planet's surface at speeds measured in centimeters per year. Liquid iron flows through the outer core in patterns that will maintain the magnetic field for billions of years into the future. Heat continues to flow upward from the deep interior, driving the geological processes that renew the surface and maintain the conditions necessary for life. The Earth beneath us is not a static, unchanging foundation, but a dynamic system in constant, gentle motion. Every breath you take, every step you make, occurs on a planet where solid rock flows like thick liquid over geological time, where liquid metal generates invisible fields that extend far into space, where heat and pressure create conditions more extreme than anything found at the surface, yet all operating according to physical laws that maintain the stable, nurturing environment we call home. The story of our planet's deep interior unfolds through the patient work of scientists who have spent decades learning to read the Earth's hidden language. Since no human instrument can journey to the planet's center and return, researchers have developed ingenious ways to peer into the darkness below, using the Earth itself as both laboratory and teacher. Every earthquake that shakes the ground sends waves rippling through the entire planet, and these seismic waves carry information about every layer they pass through. Like light bending as it moves from air into water, seismic waves change speed and direction as they encounter different materials deep inside the Earth. By carefully measuring how long these waves take to travel and how their paths curve through the planet's interior, scientists can map structures thousands of kilometers below the surface with remarkable precision. The global network of seismometers that monitors these waves operates continuously, recording thousands of earthquakes each year. Each earthquake provides a new perspective on the Earth's interior, gradually building a three-dimensional picture of the hidden world below. Over decades of patient observation, this technique has revealed the basic structure of the planet's layers, the flow patterns in the liquid core, and even the existence of mysterious formations at the boundary between the mantle and core. Laboratory experiments complement these seismic studies by recreating the extreme conditions found deep inside the Earth. Using diamond anvil cells, devices that can squeeze tiny samples between the points of industrial diamonds, scientists can subject materials to pressures millions of times greater than atmospheric pressure. Combined with laser heating, these experiments can simulate the conditions found at any depth within the planet, allowing researchers to observe how rocks and metals behave under circumstances impossible to experience at the surface. These high-pressure experiments have revealed how minerals transform as they sink deeper into the Earth, taking on new crystal structures that are stable only under extreme pressure. They've shown how iron becomes magnetic under the conditions found in the inner core, and how the electrical conductivity of liquid iron changes with temperature and pressure. Each discovery helps scientists interpret the seismic observations and understand the physical processes operating in the deep Earth. Computer models weave together the insights from seismic studies and laboratory experiments, creating virtual Earths that scientists can manipulate and observe. These numerical simulations solve the complex equations governing heat flow, fluid motion, and magnetic field generation, predicting how the Earth's interior should behave under different conditions. By comparing these predictions with real observations, researchers can test their understanding and refine their models of deep Earth processes. The magnetic field surrounding our planet provides another window into the core's behavior. Satellites orbiting high above the surface continuously measure the strength and direction of the magnetic field, tracking how it changes over time. These changes reflect the evolution of flow patterns in the liquid outer core, allowing scientists to map the circulation of molten iron thousands of kilometers below. Ground-based observatories have been monitoring the magnetic field for centuries, creating a long-term record of how the geodynamo operates and changes. Ancient rocks preserve the memory of the magnetic field's past behavior. As volcanic rocks cool and solidify, they lock in the direction of the magnetic field present at the time of their formation. By studying rocks of different ages around the world, scientists have discovered that the magnetic field has reversed its polarity many times throughout Earth's history, with north and south magnetic poles switching places over periods of thousands to millions of years. These paleomagnetic studies reveal that the Earth's magnetic field has been active for at least 3.5 billion years, protecting the atmosphere and maintaining conditions suitable for life throughout most of our planet's history. The field has varied in strength and has occasionally weakened during polarity reversals, but it has never disappeared entirely, continuing to shield the surface from harmful solar radiation. Recent technological advances have allowed scientists to probe ever deeper into the Earth's structure and behavior. Seismic tomography, similar to medical CT scanning, but applied to the entire planet, creates detailed three-dimensional images of temperature and composition variations throughout the mantle. These images reveal the locations of hot mantle plumes rising from the core mantle boundary and cold slabs of oceanic crust sinking into the deep mantle. Mineral physics experiments using synchrotron X-ray sources can now examine the atomic structure of materials under extreme pressure and temperature conditions. These studies have discovered new mineral phases that exist only in the deep Earth and have revealed how the properties of familiar minerals change under the conditions found hundreds or thousands of kilometers below the surface. The integration of all these observational and experimental techniques has revolutionized our understanding of the Earth's interior over the past few decades. What once seemed like an inaccessible realm has become increasingly well mapped and understood, though many mysteries remain. Each new discovery adds another piece to the puzzle of how our planet works as an integrated system. One of the most significant recent discoveries has been the identification of large-scale chemical variations in the deep mantle. Seismic studies have revealed that the mantle is not chemically uniform, as was once assumed, but contains regions with distinctly different compositions. These variations may represent ancient materials that have been preserved in the deep Earth for billions of years, providing clues about the planet's early history and evolution. The study of noble gases in volcanic rocks has provided additional evidence for chemical reservoirs in the deep mantle. Helium and neon isotopes found in some volcanic eruptions have signatures that suggest they originated in parts of the mantle that have remained isolated from surface processes for billions of years. These chemical fingerprints help scientists understand how the Earth has evolved chemically over geological time and how different reservoirs of material have been mixed or kept separate. Water plays a surprising and important role in the deep Earth. Even though the extreme temperatures would instantly vaporize any liquid water at the surface, water molecules can be incorporated into the crystal structure of high-pressure minerals, allowing significant amounts of water to be transported deep into the mantle by subducting oceanic plates. This water affects the physical properties of mantle rocks, making them more deformable and potentially influencing convection patterns. The discovery of water-bearing minerals that are stable under deep mantle conditions has revealed that the Earth's interior may contain vast amounts of water, possibly several times more than exists in all the oceans combined. This deep water cycle connects the surface and interior over geological timescales, influencing everything from volcanic eruptions to the long-term evolution of the oceans and atmosphere. Temperature variations throughout the Earth's interior drive all the dynamic processes that make our planet geologically active. Heat flows continuously from the hot interior toward the cold surface of space, powering mantle convection, core circulation, and plate tectonics. This heat comes from several sources that operate on different timescales and continue to warm the planet's interior billions of years after its formation. The largest contribution comes from the gradual cooling of the planet itself. When the Earth formed 4.5 billion years ago through the collision and accretion of countless smaller bodies, the energy of these impacts heated the planet to temperatures high enough to melt rock and metal. Much of this primordial heat remains trapped in the Earth's interior, slowly escaping to space over geological time. The rate of cooling is so gradual that the planet will remain hot inside for billions of years into the future. Radioactive decay provides an ongoing source of heat that will continue as long as radioactive elements remain in the Earth's interior. Uranium, thorium, and potassium atoms scattered throughout the planet decay at predictable rates, releasing energy as they transform into more stable elements. This radioactive heating is most concentrated in the continental crust and mantle, where these elements are more abundant than in the iron-rich core. Additional heat comes from the crystallization of iron onto the growing inner core. As the Earth continues to cool, liquid iron in the outer core slowly solidifies at the boundary with the inner core, releasing latent heat in the process. This heat source will continue to operate as long as the outer core remains liquid, providing energy to drive the convection that generates the magnetic field. The gravitational energy released when dense materials sink toward the planet's center also contributes to the internal heat budget. When heavy elements separate from lighter ones and sink deeper into the Earth, gravitational potential energy is converted to heat. This process was most important during the early history of the planet, when major differentiation events separated the metallic core from the rocky mantle, but it continues today on a smaller scale as chemical differentiation proceeds within each layer. Heat flows from the Earth's interior at a rate of about 44 trillion watts, roughly twice the rate at which human civilization currently consumes energy. This heat flow drives the geological processes that continuously reshape the planet's surface, from the slow movement of continents to the explosive eruptions of volcanoes. The rate of heat flow varies from place to place on the surface, being highest at mid-ocean ridges where new oceanic crust forms, and lowest in the stable interiors of old continents. The temperature structure of the Earth's interior reflects the balance between heat generation and heat transport. In the core, where heat is generated primarily by cooling and crystallization, temperatures remain relatively uniform due to efficient convective mixing. In the mantle, where heat is generated by radioactive decay and transported primarily by solid-state convection, temperature increases gradually with depth along a curve determined by the physics of heat transport in solid rock. These temperature variations create the density differences that drive convective flow throughout the Earth's interior. Hot materials are less dense and tend to rise, while cold materials are denser and tend to sink. This simple principle drives the complex circulation patterns in both the liquid outer core and the solid mantle, creating the flows that generate the magnetic field and move the tectonic plates. The study of heat flow and temperature distribution in the Earth's interior requires careful integration of many different types of observations and theoretical calculations. Seismic wave speeds depend on temperature, so seismic tomography can map temperature variations throughout the mantle. Laboratory measurements of how heat conducts through different minerals under high pressure provide the data needed to calculate temperature profiles. Observations of surface heat flow and volcanic temperatures provide constraints on the thermal state of the shallow interior. Computer models of mantle convection solve the equations governing heat transport and fluid flow to predict how temperature should vary throughout the Earth's interior. These models must account for the complex ways that temperature affects the physical properties of rocks, including their density, viscosity, and ability to conduct heat. The models also must incorporate the effects of mineral phase transitions, which can either absorb or release heat as pressure and temperature change with depth. The results of these thermal studies reveal that the Earth's interior is cooling very slowly, losing heat at a rate that will allow geological activity to continue for billions of years into the future. The cooling is so gradual that the temperature changes over human timescales are negligible, ensuring that the geological processes we observe today will continue essentially unchanged for countless generations. This thermal evolution has important implications for the long-term habitability of our planet. The heat-driving mantle convection controls the rate at which carbon is cycled between the solid Earth and the atmosphere through volcanic emissions and weathering processes. The magnetic field generated by core convection protects the atmosphere from erosion by the solar wind. The gradual cooling of the interior ensures that these vital processes will continue to operate, maintaining Earth as a habitable world far into the future. The deep Earth operates as an integrated system where processes in different layers influence each other in complex ways. Changes in the core affect the mantle through variations in heat flow and magnetic field generation. Changes in the mantle affect the core through the thermal boundary conditions at the core-mantle boundary. Both the core and mantle influence surface processes through their effects on volcanism, tectonics, and the magnetic field. This coupling between different parts of the Earth system operates over a vast range of timescales. Some processes, like the generation of seismic waves, occur almost instantaneously. Others, like the circulation of material through the entire mantle, take hundreds of millions of years to complete. The magnetic field can change direction over thousands of years, while the overall cooling of the planet proceeds over billions of years. Understanding these connections requires studying the Earth as a whole system rather than focusing on individual layers in isolation. Modern geophysics increasingly emphasizes this integrated approach, using observations from many different disciplines to build comprehensive models of how the planet works. This holistic perspective reveals the deep interconnections between processes that might seem unrelated when studied separately. The circulation of material between different layers creates pathways for chemical exchange that operate over geological timescales. Elements that start at the surface can eventually reach the core-mantle boundary through subduction and mantle convection. Material from the deep mantle can return to the surface through volcanic eruptions. These exchanges help maintain the chemical balance needed for long-term planetary habitability. The Earth's internal dynamics also influence climate and environmental conditions on timescales ranging from thousands to millions of years. Changes in the rate of volcanism affect atmospheric composition. Changes in the configuration of continents influence ocean circulation and climate patterns. Changes in the magnetic field affect the amount of cosmic radiation reaching the surface. All of these effects are ultimately driven by processes occurring deep inside the planet. Recent research has revealed that the Earth's interior preserves a record of events that occurred billions of years ago. Chemical signatures in mantle rocks provide evidence for the composition of the early atmosphere and oceans. Variations in the magnetic field recorded in ancient rocks reveal how the core has evolved over geological time. The structure of the core-mantle boundary may preserve evidence for giant impacts that occurred during the planet's formation. This deep time perspective shows that the Earth's interior has been remarkably stable over geological history, maintaining the conditions needed for life despite dramatic changes in surface environments. The same basic processes that operate today have been operating for billions of years, providing the geological foundation for the evolution and persistence of life on our planet. The study of the deep Earth continues to reveal new surprises and complexities that challenge our understanding of planetary processes. Each new discovery adds another layer to our appreciation of the remarkable system that operates beneath our feet, maintaining the stable, nurturing environment that makes Earth unique among the planets of our solar system. As we've explored this hidden world together, moving slowly through layers of rock and metal that exist in conditions more extreme than anything we experience at the surface, a profound picture emerges of our planet as a living system. The Earth beneath us is not a cold, dead foundation. but a dynamic, breathing entity where solid rock flows like honey over millions of years, where liquid metal dances in patterns that create invisible shields extending far into space, where heat and pressure forge conditions that would be alien to surface dwellers, yet all working in perfect harmony to maintain the gentle world we call home. Every step you take rests upon continents that are slowly drifting across the planet's surface. Every breath you draw is protected by a magnetic field generated by flows of molten iron thousands of kilometers below. The ground that feels so solid and permanent beneath your feet is actually in constant, patient motion, participating in geological processes that have been maintaining Earth's habitability for billions of years and will continue to do so for billions more. This vast, slow symphony of stone and metal, heat and magnetism continues its ancient rhythm while you sleep, while you dream, while you rest peacefully on the surface. The earth cradles you gently, its deep processes working with the same patient persistence they have shown since the first sunrise, ensuring that when you wake, the world will still be here, still stable, still nurturing, still home. In the darkness below, in chambers no human eye will ever see, the quiet heart of our world beats on, steady and eternal, keeping time with the pulse of geological ages, a rhythm as reliable as the turning of the stars themselves. Right now, deep beneath the surface where you rest, the Earth's interior continues its ancient work with the same steady patience it has shown for over 4 billion years. The processes we've explored together, from the flowing currents of liquid iron in the outer core to the gentle circulation of solid rock in the mantle, represent just the beginning of a story that unfolds across timescales so vast they encompass the entire history of life itself. In the deepest reaches of the planet, where pressures exceed anything we can truly comprehend, and temperatures rival the surface of distant stars, iron and nickel exist in states that would be impossible anywhere else in our solar system. The inner core, that solid metallic sphere suspended in an ocean of liquid metal, grows imperceptibly larger each day as more iron crystallizes from the surrounding liquid. This growth, measured in fractions of millimeters per year, represents one of the most consistent and predictable processes on our planet. The energy released by this crystallization sends ripples of heat upward through the liquid outer core, driving the complex flows that have maintained Earth's magnetic field for billions of years. These currents of molten metal, each one larger than entire continents, move through the darkness of the deep Earth with a precision and consistency that would be beautiful to witness if human eyes could somehow peer into that hidden realm. Scientists studying these deep processes have discovered that the magnetic field protecting us varies in strength and direction over time, but it has never failed in its essential purpose. Throughout the ages when dinosaurs roamed the surface, when the first plants colonized the land, when the earliest life forms were taking their first tentative steps in ancient oceans, the magnetic field has been there, an invisible guardian generated by processes so deep and so remote that they operate entirely independent of anything happening at the surface. The heat that drives these processes comes from sources that will continue operating long after human civilization has become part of the geological record. Radioactive elements scattered throughout the Earth's interior decay with mathematical precision, each atom releasing its stored energy according to physical laws that have remained constant since the formation of the universe. Uranium atoms that were forged in the heart of dying stars billions of years before our solar system existed continue to warm the planet from within, their slow decay providing a steady source of energy that will persist for billions of years into the future. This radioactive heating is distributed throughout the planet's interior, but it is most concentrated in the rocky layers of the mantle and crust, where these heavy elements became concentrated during the planet's formation. Every second, trillions upon trillions of these atomic transformations release tiny amounts of energy that collectively warm vast regions of rock, maintaining the temperature gradients that drive convection and keep the Earth geologically active. The interplay between this internal heating and the planet's steady cooling to space creates the thermal engine that powers everything we observe at the surface. Hot rock rises slowly through the mantle while cooler rock sinks, creating circulation patterns that have been operating since the planet first differentiated into distinct layers. These patterns change and evolve over geological time, but their basic character remains remarkably consistent. Recent advances in our understanding of these processes have revealed that the Earth's interior is even more complex and dynamic than scientists once imagined. The discovery of the donut-shaped structure in the outer core suggests that the boundary between liquid metal and solid rock influences convection patterns in ways that are only beginning to be understood. This structure, parallel to the Earth's equator and extending for thousands of kilometers through the liquid core, affects how seismic waves travel through the region and provides new clues about the intricate physics governing the geodynamo. The existence of such structures reminds us that the Earth's interior is not a simple system with uniform properties, but rather a complex and evolving environment where different regions have distinct characteristics that have developed over billions of years of planetary evolution. The large, low shear velocity provinces at the core mantle boundary, those continent-sized formations of unusual material, may represent some of the oldest features on our planet, preserving chemical signatures from the earliest days of Earth's history. These ancient structures influence how heat flows from the core into the overlying mantle, creating variations in temperature that propagate upward through thousands of kilometers of rock. Where heat flow is enhanced, mantle plumes begin their slow journey toward the surface, eventually creating volcanic hotspots that can persist for tens of millions of years. Where heat flow is reduced, the mantle circulation patterns adjust, creating different pathways for the transport of material and energy. The Hawaiian island chain, stretching across thousands of kilometers of Pacific Ocean floor, provides a beautiful example of how deep Earth processes manifest at the surface. The volcanic hotspot responsible for creating these islands has been active for over 70 million years, fed by a mantle plume that rises from the core mantle boundary nearly 3,000 kilometers below. As the Pacific plate moves slowly northwest over this stationary heat source, new volcanoes form, while older ones become extinct and are carried away from their source of magma. This process operates with such regularity that scientists can use the spacing and ages of the volcanic islands to calculate the speed and direction of plate motion over geological time. The trail of extinct volcanoes and seamounts extending northwest from the currently active Hawaiian volcanoes tells the story of how the Pacific plate has moved over the past 70 million years, providing a record of tectonic motion that spans the entire age of mammals on Earth. Similar hotspot tracks exist around the world, each one documenting the patient movement of continents and ocean floor over stationary plumes of hot mantle rock. The Yellowstone region of North America sits above a plume that has left a trail of ancient volcanic calderas across the western United States, marking the passage of the North American continent over the hotspot during the past 17 million years. Iceland occupies a unique position where a mantle plume intersects the mid-Atlantic ridge, creating one of the most volcanically active regions on Earth and contributing to the ongoing separation of Europe and North America. These hotspots represent just one way that deep Earth processes influence the surface environment. The more widespread and fundamental process of plate tectonics is driven by the overall circulation of the mantle, which creates forces that pull oceanic plates apart at mid-ocean ridges and push them together at subduction zones. This global system of moving plates has been operating for at least 3 billion years, continuously recycling oceanic crust and reshaping the configuration of continents. The rock that forms at mid-ocean ridges today will eventually travel across ocean basins and be subducted back into the mantle at distant continental margins, completing a cycle that typically takes 1 to 200 million years. During this journey, The oceanic crust accumulates sediments from the overlying ocean, incorporates chemical signatures from seawater, and sometimes captures pieces of continents or oceanic plateaus. When this material finally descends into the mantle, it carries with it a record of surface conditions that existed when it first formed. This subducted material sinks slowly through the mantle, eventually reaching the core mantle boundary, where it may remain for hundreds of millions of years before being incorporated into rising mantle plumes and eventually returning to the surface through volcanic eruptions. The chemical signatures preserved in this recycled material provide clues about ancient environments, including the composition of early oceans and atmospheres that existed billions of years ago. The timescales involved in this deep recycling process are almost impossible to comprehend from a human perspective. Rock that is currently being subducted beneath the Andes or the Japanese islands will not return to the surface for hundreds of millions of years, by which time the continents will have moved to entirely different positions and life on Earth will have evolved in ways we cannot imagine. Yet this same process has been operating throughout Earth's history, continuously mixing materials between the surface and deep interior. Water plays a crucial role in these deep Earth processes, even though the extreme temperatures and pressures would instantly vaporize any liquid water at the surface. Water molecules can be incorporated into the crystal structure of high-pressure minerals, allowing oceanic plates to transport significant amounts of water into the deep mantle. This water affects the physical properties of mantle rocks, making them more deformable and lowering their melting temperatures. The amount of water stored in the Earth's interior may be enormous, possibly several times greater than the volume of all surface oceans combined. This water is not present as liquid, but rather as hydroxyl groups incorporated into mineral crystals, or as water molecules trapped in high-pressure mineral structures. Recent laboratory experiments have identified new water-bearing minerals that are stable under the extreme conditions of the deep mantle, suggesting that water can be transported to great depths within the Earth. This deep water cycle operates over geological timescales, connecting the surface hydrosphere with the planet's interior through the processes of subduction and volcanism. Water carried into the mantle by subducting plates can eventually return to the surface through volcanic eruptions, sometimes after spending hundreds of millions of years in the deep Earth. The rate of water exchange between the surface and interior influences the long-term evolution of the oceans and atmosphere, helping to regulate global climate over geological time. The study of these processes requires sophisticated techniques that can probe the Earth's interior without direct access to the deep layers. Seismic tomography, the three-dimensional imaging of the Earth's interior using earthquake waves, has revealed the complex structure of mantle circulation patterns. These images show cold slabs of subducted oceanic crust sinking through the mantle and hot plumes of rock rising from the core mantle boundary, providing direct evidence for the convection patterns that drive plate tectonics. Advanced laboratory experiments using diamond anvil cells and synchrotron X-ray sources can now recreate the pressures and temperatures found throughout the Earth's interior, allowing scientists to study how materials behave under these extreme conditions. These experiments have revealed new mineral phases that exist only in the deep Earth and have provided crucial data for interpreting seismic observations and understanding the physics of mantle convection. Computer models that solve the complex equations governing heat transport, fluid flow, and chemical evolution in the Earth's interior help integrate observations from many different sources into comprehensive pictures of how the planet works. These models can predict how the Earth's interior should evolve over time and can be used to test different hypotheses about deep Earth processes. The magnetic field that surrounds our planet provides another window into the behavior of the deep interior. Satellites orbiting high above the surface continuously monitor the strength and direction of the magnetic field, tracking how it changes as the circulation patterns in the liquid outer core evolve. These changes occur over timescales of years to decades, much faster than most geological processes, providing a real-time view of dynamics in the deep Earth. Ground-based magnetic observatories have been monitoring the magnetic field for centuries, creating a long-term record that reveals how the geodynamo operates and changes over time. This record shows that the magnetic field undergoes continuous variations in strength and direction, with occasional dramatic events such as polarity reversals when the north and south magnetic poles switch places. The most recent magnetic reversal occurred about 780,000 years ago, and the current weakening of the magnetic field in some regions suggests that another reversal might occur within the next few thousand years. However, even during reversals, the magnetic field does not disappear entirely, but rather becomes more complex, with multiple magnetic poles and reduced overall strength. Throughout these changes, the field continues to provide protection from solar radiation, ensuring that surface conditions remain suitable for life. Paleomagnetic studies of ancient rocks reveal that the magnetic field has been operating for at least 3.5 billion years, providing continuous protection for the atmosphere and surface environment throughout most of Earth's history. This remarkable stability of the geodynamo reflects the fundamental physics governing convection in the liquid outer core and the steady supply of energy from the cooling and crystallization of the inner core. The heat driving all these processes flows continuously from the Earth's interior toward the cold vacuum of space, carrying energy at a rate of about 44 trillion watts. This heat flow powers the geological processes that maintain Earth as an active, dynamic planet, distinguishing it from smaller bodies like the Moon and Mars that have largely cooled and become geologically inactive. The rate of heat loss is so gradual that the Earth will remain thermally active for billions of years into the future. Computer models of the planet's thermal evolution predict that mantle convection will continue operating, the magnetic field will persist, and volcanism will continue shaping the surface for at least another 4 to 5 billion years. This enormous timescale ensures that the geological processes maintaining Earth's habitability will continue operating long after the Sun begins its evolution toward becoming a red giant star. The deep Earth thus represents one of the most stable and persistent systems in our solar system, maintaining the conditions necessary for life through continuous operation over geological time. The processes we have explored together, from the circulation of liquid iron in the outer core to the slow convection of solid rock in the mantle, work together to create and maintain the environment that makes Earth unique among the planets. Recent discoveries continue to reveal new aspects of this hidden world beneath our feet. The identification of new mineral phases that exist only under extreme pressure, the mapping of chemical variations in the deep mantle, and the discovery of structures like the donut-shaped region in the outer core all point toward a deep Earth that is more complex and dynamic than previously imagined. Future research will undoubtedly reveal additional surprises as techniques for studying the Earth's interior continue to improve. New seismic networks will provide higher resolution images of internal structure. Advanced laboratory experiments will recreate ever more extreme conditions, helping scientists understand the behavior of materials at the center of the planet. Computational models will become more sophisticated, incorporating increasingly detailed physics to predict how the Earth's interior evolves over time. Each new discovery adds to our appreciation of the remarkable system operating beneath the surface, a system that has maintained the stable, nurturing environment we call home for billions of years. The Earth's interior is not a static, unchanging foundation, but rather a dynamic living system where matter and energy flow in patterns that connect the deepest core with the surface where we live. As we reach the end of our journey together through the hidden layers of our planet, it's worth reflecting on the profound timescales over which these processes operate. The rock beneath your feet has been on journeys that span hundreds of millions of years, traveling from ocean ridges to subduction zones, sinking deep into the mantle, and eventually returning to the surface through volcanic eruptions. The iron flowing in the outer core has been circulating for billions of years, generating the magnetic field that has protected life throughout its entire evolution on Earth. These processes continue right now, at this very moment, with the same patient persistence they have shown throughout geological history. The mantle convects, the core circulates, heat flows upward from the deep interior, and the magnetic field extends far into space, all operating according to physical laws that will ensure their continuation for billions of years into the future. The Earth beneath us is not merely a platform for life, but an active participant in maintaining the conditions that make life possible. The carbon cycle that regulates global climate operates through the exchange of materials between the surface and deep interior. The magnetic field that protects the atmosphere is generated by processes occurring thousands of kilometers below the surface. The gradual cooling of the planet provides the energy needed to maintain geological activity that renews the surface and supplies volcanic gases to the atmosphere. In this vast interconnected system, every layer influences every other layer, creating a planetary environment that has remained remarkably stable over geological time, despite dramatic changes in surface conditions. The same basic processes that maintain Earth's habitability today have been operating since the earliest days of life on our planet, providing the geological foundation for evolution and the persistence of living systems. As you rest on the surface of this remarkable world, surrounded by the quiet rhythms of night, remember that you are cradled by a planet that is alive with motion and energy, where solid rock flows like honey over millions of years, where liquid metal dances in patterns that create invisible shields, extending far into space, where the very atoms that make up the deep interior continue the slow transformations that have been warming our world for billions of years. These processes operate with a patience and persistence that transcends all human timescales, following patterns established in the earliest days of our planet's formation, and continuing into a future so distant it encompasses countless generations of stars. The Earth holds you gently in its gravitational embrace, its deep currents of rock and metal, working steadily to maintain the stable, nurturing environment that makes this moment possible. In the darkness below, in chambers of stone and metal that exist under pressures and temperatures beyond anything we experience at the surface, the quiet heart of our world continues its ancient work. Heat flows upward through thousands of kilometers of rock, carrying energy from the deep interior toward the surface where it escapes to space. Liquid iron circulates in vast patterns that generate the magnetic field protecting all life above. Solid rock moves in currents so slow they are imperceptible to human observation, yet so powerful they shape continents and ocean basins over geological time. This vast symphony of geological processes operates beyond the reach of human senses, yet its effects surround us completely. Every breath you take exists within the magnetic field generated by the core. Every step you make rests upon continents that drift slowly across the planet's surface. Every moment of your life unfolds on a world where the deep interior maintains the conditions necessary for the existence of liquid water, a stable atmosphere, and the complex chemistry of life itself. The Earth cradles humanity with the same gentle persistence it has shown to countless generations of living beings throughout the planet's history. The geological processes that maintained conditions suitable for the first simple cells continue to operate today, ensuring that the surface remains a hospitable environment for the complex communities of life that have evolved over billions of years of Earth history. As you settle into rest, let the knowledge of these deep, patient processes bring a sense of profound stability and continuity. Beneath the temporary concerns and rapid changes of human life lies something vast and enduring, a planetary system that has been maintaining the foundations of existence for longer than life has existed on Earth. The ground beneath you is solid and reliable, not because it is static, but because it participates in geological processes so fundamental and persistent that they provide the ultimate foundation for everything we know and experience. The Earth breathes slowly with the rhythm of geological time, its deep circulation patterns moving with the patience of eons. its magnetic field pulsing gently with changes that unfold over centuries and millennia. This vast, slow heartbeat of the planet continues while you rest, while you dream, while you sleep peacefully on the surface of a world that is alive with quiet motion in its deepest places. In chambers of rock and metal that no human eye will ever see, where temperatures exceed those found on the surface of distant stars and pressures would instantly crush any material from the surface world, the Earth maintains the gentle processes that make this moment possible. The inner core grows imperceptibly larger, releasing heat that drives the circulation of liquid iron above. The outer core flows in patterns of exquisite complexity, generating the invisible field that extends far beyond the atmosphere. The mantle rises and falls in currents that span continents, slowly reshaping the surface geography over millions of years. All of these processes work together to maintain Earth as a stable, nurturing environment, a rare oasis of complexity and life in a universe where most worlds are cold, dead, and sterile. The deep Earth ensures that liquid water can exist at the surface, that the atmosphere remains bound to the planet, that the chemical cycles necessary for life continue to operate over geological time. As you rest in the quiet darkness of night, you are held gently by a planet that is itself resting in the vast darkness of space, its internal fires burning steadily, its magnetic field extending like an invisible embrace that protects everything within its reach. The Earth spins slowly on its axis, carrying you through the cosmic night, while its deep interior continues the ancient work that has been maintaining conditions suitable for life since before the first sunrise illuminated this world. The story of the deep Earth is ultimately a story of patience and persistence, of processes so fundamental and reliable that they have operated continuously for billions of years, creating and maintaining the stable environment that makes all other stories possible. In the depths below, in the eternal darkness where no light has ever shone, the quiet heart of our world beats on, steady and eternal, keeping time with the rhythm of geological ages, a pulse as reliable as the turning of the stars themselves. Of the stars themselves, the story of how we came to understand these hidden depths is itself a testament to human curiosity and patience. For most of human history, the earth beneath our feet remained completely mysterious. Ancient peoples could only wonder what lay below the deepest wells and mines, creating myths and stories to explain the occasional earthquake or volcanic eruption that reminded them of the hidden world below. The first real glimpse into the Earth's interior came from a most unexpected source. In 1890, a Croatian scientist named Andrija Mohorovičić was studying earthquake records when he noticed something curious. Seismic waves from distant earthquakes seemed to change speed as they traveled through the Earth, as if they were encountering different materials at different depths. This observation led to the discovery of the boundary between the Earth's crust and mantle, a transition zone now known as the Mohorovičić discontinuity, or simply the MOHO. This discovery revealed that the Earth was not a uniform sphere of rock, but rather a layered structure with distinct regions of different composition and properties. Over the following decades, seismologists around the world began to map these layers by carefully studying how earthquake waves behaved as they traveled through the planet. Each earthquake provided new information, gradually building a picture of the Earth's internal architecture. The breakthrough that revealed the liquid nature of the outer core came from a Danish seismologist named Inger Lehmann in 1936. She noticed that certain types of seismic waves, called shear waves, disappeared when they tried to pass through a particular region deep inside the Earth. Since shear waves cannot travel through liquids, this observation provided the first definitive evidence that part of the Earth's core was molten. Lehmann's careful analysis also revealed the existence of the solid inner core, a discovery that revolutionized our understanding of the planet's structure. These early discoveries were made possible by the global network of seismographs that began to be established in the late 19th and early 20th centuries. Each station recorded the arrival times and characteristics of seismic waves from earthquakes around the world, creating a vast database of information about how these waves traveled through the Earth's interior. The analysis of this data required patience and mathematical skill, as scientists had to work backwards from the observed wave patterns to infer the properties of the materials the waves had encountered. The development of more sensitive instruments in the mid-20th century allowed scientists to detect much smaller earthquakes and to measure seismic waves with greater precision. This led to the discovery of additional layers and boundaries within the Earth, including the transition zone in the mantle, where pressure causes minerals to transform into denser crystal structures. Each new discovery added another piece to the puzzle of the Earth's internal structure. Computer technology revolutionized the study of the Earth's interior in the latter half of the 20th century. For the first time, scientists could process vast amounts of seismic data simultaneously, creating three-dimensional images of the Earth's internal structure through a technique called seismic tomography. These images revealed that the mantle was not uniform, but contained regions of different temperature and composition that reflected the complex patterns of convection operating within the Earth. Modern seismology uses networks of thousands of instruments around the world, each capable of detecting ground motion smaller than the width of an atom. When an earthquake occurs anywhere on Earth, waves from that event are recorded by stations around the globe, providing multiple perspectives on how the waves have traveled through the planet's interior. Sophisticated computer algorithms process this data to create detailed maps of temperature, composition, and flow patterns throughout the Earth. Laboratory experiments complement these seismic studies by recreating the extreme conditions found in the Earth's interior. Using devices called diamond anvil cells, scientists can squeeze tiny samples of rock and metal to pressures millions of times greater than atmospheric pressure while heating them to temperatures of thousands of degrees. These experiments reveal how materials behave under the conditions found at different depths within the Earth, providing the physical understanding needed to interpret seismic observations. Recent advances in experimental techniques have allowed scientists to study materials under conditions equivalent to those found at the very center of the Earth. Synchrotron X-ray sources, which produce incredibly bright and focused X-ray beams, can probe the atomic structure of materials under extreme pressure and temperature. These studies have revealed new mineral phases that exist only in the deep Earth and have provided insights into how the physical properties of familiar materials change under extreme conditions. The study of meteorites provides another window into the Earth's interior. Iron meteorites, which are thought to be fragments of the cores of ancient asteroids, give us examples of metal similar to that found in the Earth's core. By studying these samples, scientists can understand how iron and nickel behave under high pressure and temperature, providing clues about the processes operating in the Earth's core. Computer models play an increasingly important role in understanding the Earth's interior. These models solve the complex equations governing heat transfer, fluid flow, and magnetic field generation, predicting how the Earth's interior should behave under different conditions. By comparing the predictions of these models with real observations, scientists can test their understanding of deep Earth processes and refine their theories. The magnetic field surrounding our planet provides a unique opportunity to study the Earth's core in real time. Unlike most geological processes, which operate over millions of years, the magnetic field changes on timescales of years to decades as the flow patterns in the liquid outer core evolve. Satellites orbiting high above the surface continuously monitor these changes, providing a real-time view of dynamics in the deep Earth. Ground-based magnetic observatories have been recording the Earth's magnetic field for centuries, creating a long-term record of how the field has changed over time. This record shows that the magnetic field undergoes continuous variations, with occasional dramatic events such as polarity reversals when the north and south magnetic poles switch places. The study of these changes helps scientists understand how the geodynamo operates and how it might change in the future. Ancient rocks preserve a record of the magnetic field's behavior over geological time. As volcanic rocks cool and solidify, they lock in the direction of the magnetic field present at the time of their formation. By studying rocks of different ages around the world, scientists have discovered that the magnetic field has been active for at least 3.5 billion years and has undergone hundreds of polarity reversals throughout Earth's history. The integration of all these different approaches, from seismic studies to laboratory experiments to magnetic field observations, has created a comprehensive picture of the Earth's interior that continues to evolve as new discoveries are made. Each technique provides a different perspective on the deep Earth, and it is only by combining these multiple viewpoints that scientists can understand the complex processes operating in the planet's hidden depths. Recent discoveries continue to surprise scientists and reveal new aspects of the Earth's interior. The identification of the donut-shaped structure in the outer core, the discovery of vast water reservoirs in the deep mantle, and the mapping of ancient chemical signatures preserved at the core mantle boundary all point toward a deep Earth that is more complex and dynamic than previously imagined. These ongoing discoveries remind us that the Earth's interior remains largely mysterious despite centuries of scientific investigation. Each new observation raises additional questions about the processes operating in the deep Earth, ensuring that the study of our planet's hidden layers will continue to be an active area of research for generations to come. The patient work of scientists around the world, combining observations from many different sources and techniques, gradually builds our understanding of the vast system operating beneath our feet. This understanding reveals the Earth not as a static, unchanging foundation, but as a dynamic, living planet, where matter and energy flow in patterns that connect the deepest interior with the surface where we live. The heat that drives all these deep Earth processes flows continuously upward from the interior, following pathways that have been established over billions of years of planetary evolution. This heat comes from several sources that operate on different timescales, creating a thermal engine that will continue operating for billions of years into the future. The largest component of the Earth's internal heat comes from the gradual cooling of the planet itself. When the Earth formed through the collision and accretion of countless smaller bodies, the energy released by these impacts heated the planet to temperatures high enough to melt rock and metal. This primordial heat became trapped in the Earth's interior, where it has been slowly escaping to space ever since. The rate of cooling is extraordinarily gradual because rock and metal are poor conductors of heat. Heat must travel through thousands of kilometers of solid material to reach the surface, a journey that takes hundreds of millions of years. The Earth acts like a vast thermal reservoir, storing enough heat to maintain geological activity for billions of years beyond the current age of the planet. Radioactive decay provides an additional source of heat that will continue as long as radioactive elements remain in the Earth's interior. Uranium, thorium, and potassium atoms scattered throughout the planet decay at predictable rates, releasing energy as they transform into more stable elements. This process operates according to the immutable laws of nuclear physics, providing a steady and reliable source of internal heating. The heat generated by radioactive decay is not evenly distributed throughout the Earth. These elements are more abundant in the rocky layers of the crust and mantle than in the metallic core, creating variations in heat production that influence convection patterns and the overall thermal structure of the planet. Continental crust, in particular, contains relatively high concentrations of radioactive elements, contributing to the complex patterns of heat flow observed at the Earth's surface. The crystallization of iron onto the growing inner core provides another source of heat that operates as the Earth continues to cool. When liquid iron solidifies, it releases latent heat, just as water releases heat when it freezes. This process occurs continuously at the boundary between the liquid outer core and solid inner core, providing energy that helps drive the convection responsible for generating the magnetic field. Gravitational energy also contributes to the Earth's internal heat budget, though this source was more important in the past than it is today. when dense materials sink toward the center of the Earth and lighter materials rise toward the surface, gravitational potential energy is converted to heat. This process was most significant during the early history of the planet, when major differentiation events separated the metallic core from the rocky mantle, but it continues today on a smaller scale. The combination of these heat sources maintains temperature gradients throughout the Earth's interior that drive the convective motions responsible for plate tectonics, volcanism, and magnetic field generation. The balance between heat generation and heat loss determines the vigor of these processes and controls the overall thermal evolution of the planet. Temperature increases steadily with depth throughout most of the Earth's interior, following curves determined by the physics of heat transport in different materials. In the crust and upper mantle, where heat is transported primarily by conduction through solid rock, temperature increases at a rate of about 25 to 30 degrees Celsius per kilometer of depth. Deeper in the mantle, where convection becomes more efficient at transporting heat, the temperature gradient becomes less steep. At the core mantle boundary, temperatures reach approximately 4,000 degrees Celsius, comparable to the surface temperature of the Sun. The liquid outer core maintains a relatively uniform temperature due to efficient convective mixing, while the solid inner core is slightly hotter due to the additional pressure at greater depth. These extreme temperatures are sustained by the continuous flow of heat from the various sources operating within the Earth's interior. The pressure conditions in the Earth's interior are equally extreme, increasing steadily with depth due to the weight of the overlying material. At the surface, atmospheric pressure is just over 1 bar, but pressure increases by approximately 1 bar for every 10 meters of depth in the solid Earth. By the time we reach the center of the planet, pressure exceeds 3.5 million bars, creating conditions that cannot be replicated in any laboratory on Earth. These extreme pressures have profound effects on the behavior of materials in the Earth's interior. Minerals that are stable at surface conditions transform into denser crystal structures as pressure increases with depth. These phase transitions occur at specific depths throughout the mantle, creating boundaries that affect how seismic waves travel through the Earth and how materials flow in response to convective forces. The transition zone of the mantle, located between depths of 400 and 660 kilometers, is characterized by several major phase transitions that dramatically affect the physical properties of mantle rocks. At these depths, the common mantle mineral olivine transforms into a series of denser structures that can accommodate the increasing pressure. These transformations absorb or release heat, affecting convection patterns and potentially creating barriers to vertical flow in the mantle. The pressure at the core mantle boundary is sufficient to compress iron to densities nearly twice that observed at surface conditions. In the inner core, where pressures are even higher, iron is squeezed into crystal structures that may be different from those stable at lower pressures. The study of iron under these extreme conditions requires sophisticated experimental techniques and theoretical calculations that push the boundaries of current scientific capabilities. Despite these extreme conditions, the materials of the Earth's interior behave according to well-understood physical principles. The high temperatures make rocks and metals more deformable, while the high pressures tend to make them stiffer. The balance between these competing effects determines how materials flow and deform in response to the forces generated by convection and gravitational settling. In the mantle, solid rock deforms and flows over geological timescales through processes similar to those that allow glacial ice to flow down mountain valleys while remaining solid. Individual atoms and crystal defects move slowly through the solid material, allowing entire rock masses to change shape and flow in response to convective forces. This process, called creep deformation, operates so slowly that it is imperceptible on human timescales, but is fundamental to the operation of plate tectonics over geological time. The liquid outer core behaves more like a conventional fluid, with iron and nickel flowing in response to thermal and rotational forces. However, the extreme pressure and temperature conditions in the core affect the physical properties of liquid iron in ways that are only beginning to be understood. The electrical conductivity of liquid iron under core conditions is much higher than that of iron at surface conditions, which has important implications for magnetic field generation. The study of material properties under extreme conditions continues to reveal new insights into the behavior of the Earth's interior. Recent experiments have discovered new phases of ice that form under extreme pressure, new mineral structures that exist only in the deep mantle, and new ways that water can be incorporated into high-pressure minerals. Each discovery adds to our understanding of the complex chemical and physical processes operating in the Earth's hidden depths. The flow of heat from the Earth's interior to the surface drives the geological processes that continuously reshape the planet's surface. This heat flow varies from place to place, being highest at mid-ocean ridges where new oceanic crust forms and lowest in the stable interiors of old continents. The total heat flow from the Earth's interior is approximately 44 trillion watts, roughly twice the rate at which human civilization currently consumes energy. This enormous heat flow powers the convection in the mantle that drives plate tectonics, the circulation in the outer core that generates the magnetic field, and the volcanism that brings material from the deep interior to the surface. The rate of heat flow has decreased slowly over geological time as the Earth has cooled, but computer models predict that it will remain sufficient to maintain geological activity for billions of years into the future. The pathways by which heat travels from the interior to the surface are complex and varied. In some regions, heat is transported primarily by conduction through solid rock, a slow process that can take hundreds of millions of years. In other regions, convection in the mantle brings hot material directly to the surface through volcanic eruptions, providing a much more rapid pathway for heat transport. The efficiency of heat transport affects the thermal structure of the Earth's interior and influences the patterns of convection that drive surface processes. Regions where heat transport is more efficient tend to have cooler interior temperatures and more vigorous convection, while regions where heat transport is less efficient tend to develop hotter interior temperatures that may eventually lead to increased volcanic activity. The study of heat flow patterns at the Earth's surface provides important constraints on models of interior structure and dynamics. Measurements of heat flow in ocean basins reveal the cooling of oceanic crust as it moves away from mid-ocean ridges. Heat flow measurements on continents reflect the complex thermal structure of continental crust and the underlying mantle, including the effects of radioactive heat production and ancient geological events. Variations in surface heat flow also provide clues about the deep structure of the mantle and the patterns of convection operating at depth. Regions of higher than average heat flow may indicate the presence of rising mantle plumes, while regions of lower heat flow may reflect the downwelling of cold material in subduction zones. The integration of heat flow data with seismic observations helps scientists understand the three-dimensional structure of mantle convection. The Earth's thermal evolution over geological time has been controlled by the balance between internal heat generation and heat loss to space. Early in the planet's history, when radioactive elements were more abundant and the Earth retained more of its primordial heat, interior temperatures were higher and geological processes were more vigorous. As the planet has cooled over billions of years, the intensity of these processes has gradually decreased. Computer models of thermal evolution predict that the Earth will continue cooling for billions of years into the future, but at such a slow rate that geological activity will persist long after the Sun begins its evolution toward becoming a red giant star. The fundamental processes that maintain the Earth as a habitable planet, including plate tectonics and magnetic field generation, appear to be stable over these enormous timescales. The thermal history of the Earth is intimately connected to the evolution of life and the development of the planet's surface environment. The gradual cooling of the interior has affected the composition of volcanic gases released to the atmosphere, the rate of carbon cycling between the solid Earth and the atmosphere, and the long-term stability of liquid water at the surface. Understanding the Earth's thermal evolution thus provides insights into the conditions that have maintained the planet as a habitable world throughout its history. The magnetic field that surrounds our planet represents one of the most remarkable and important consequences of the Earth's internal dynamics. This invisible shield extends far beyond the atmosphere, creating a protective bubble called the magnetosphere that deflects most of the charged particles streaming from the sun as the solar wind. The generation of this magnetic field through the motion of liquid iron in the outer core represents one of the most complex and fascinating processes operating in the Earth's interior. The geodynamo, as this process is known, involves the interaction between fluid motion, magnetic fields, and electrical currents in ways that are only partially understood despite decades of intensive research. The basic principle underlying the geodynamo is electromagnetic induction, the same physical process that operates in electrical generators and transformers. When electrically conductive liquid iron moves through a magnetic field, it generates electrical currents, which in turn create new magnetic fields. If the motion is organized in the right way, these new magnetic fields can reinforce and amplify the original field, creating a self-sustaining dynamo process. The challenge in understanding the geodynamo lies in the incredible complexity of the fluid motions in the outer core. The liquid iron moves in three-dimensional patterns that are influenced by the Earth's rotation, the cooling and crystallization of the inner core, thermal convection driven by heat flow from below, and the magnetic forces generated by the dynamo process itself. These different influences interact in non-linear ways that make the system extremely difficult to predict or model. Recent computer simulations of the geodynamo have succeeded in reproducing many of the observed characteristics of the Earth's magnetic field, including its overall structure, its strength, and its tendency to undergo polarity reversals. These models require enormous computational resources because they must solve the equations governing fluid motion, heat transfer, and electromagnetic fields simultaneously throughout the entire outer core. The results of these simulations reveal that the geodynamo operates in a delicate balance between different physical processes. If the convection in the outer core is too weak, the dynamo cannot generate a strong magnetic field. If the convection is too strong, the magnetic field becomes chaotic and unstable. The Earth appears to operate in an intermediate regime, where the dynamo can generate a strong, relatively stable magnetic field, while still allowing for occasional reversals and variations. The magnetic field generated by the geodynamo has a complex structure that extends throughout the outer core and far into space. Near the Earth's surface, the field resembles that of a giant bar magnet, with magnetic field lines emerging from the surface near the south geographic pole and returning to the surface near the north geographic pole. However, this simple dipolar structure becomes more complex at depth, where the field includes many smaller scale features that reflect the detailed patterns of flow in the liquid core. The strength of the magnetic field varies significantly with location and time. At the Earth's surface, the field strength ranges from about 25 microtesla near the magnetic equator to about 65 microtesla near the magnetic poles. Deep within the outer core, magnetic field strengths are estimated to be about 50 times larger, reaching values of several millitesla. The magnetic field undergoes continuous changes as the flow patterns in the outer core evolve. These changes occur over a wide range of timescales, from rapid fluctuations that can be observed over periods of months or years, to slower variations that unfold over centuries or millennia. The fastest changes are thought to be associated with waves that propagate through the liquid core, while the slower changes reflect the gradual evolution of the large-scale convection patterns. One of the most dramatic changes that the magnetic field can undergo is a polarity reversal, when the north and south magnetic poles switch places. These reversals have occurred hundreds of times throughout Earth's history, with the time between reversals ranging from thousands to millions of years. The most recent reversal occurred about 780,000 years ago. and some scientists suggest that the current weakening of the magnetic field in certain regions may indicate that another reversal is approaching. During a polarity reversal, the magnetic field does not simply flip instantaneously from one polarity to the other. Instead, the field weakens and becomes more complex, often developing multiple magnetic poles and a more chaotic structure. The reversal process typically takes several thousand years to complete, during which time the magnetic field provides reduced but still significant protection from solar radiation. The study of ancient magnetic field behavior preserved in rocks reveals that polarity reversals are a normal part of the geodynamo process and do not appear to be associated with major extinctions or environmental catastrophes. However, the reduced magnetic field strength during reversals may allow increased cosmic radiation to reach the Earth's surface, potentially affecting climate and atmospheric chemistry in subtle ways. The Earth's magnetic field plays a crucial role in maintaining the planet's habitability by protecting the atmosphere from erosion by the solar wind. Without this protection, charged particles from the Sun would gradually strip away the atmosphere over geological time, leaving the Earth as a cold, airless world like Mars. The continuous operation of the geodynamo for billions of years has been essential for maintaining the atmospheric conditions necessary for life. The interaction between the magnetic field and the solar wind creates the magnetosphere, a region of space around the Earth where the planet's magnetic field dominates over the magnetic field carried by the solar wind. The shape of the magnetosphere is determined by the balance between the pressure of the solar wind and the pressure of the Earth's magnetic field, creating a complex three-dimensional structure that extends far beyond the atmosphere. On the side of the Earth facing the Sun, the magnetosphere is compressed by the solar wind to a distance of about 10 Earth radii from the planet's center. On the side facing away from the Sun, the magnetosphere is stretched into a long tail that extends for hundreds of Earth radii into space. This asymmetric structure channels charged particles around the Earth, preventing most of them from reaching the atmosphere. Some charged particles do penetrate the magnetosphere, particularly during periods of high solar activity, when the solar wind is stronger and more turbulent. These particles can cause beautiful auroral displays when they collide with atoms in the upper atmosphere, creating the northern and southern lights that are visible at high latitudes. The auroras provide a visible reminder of the invisible magnetic field that protects our planet. The study of the Earth's magnetic field and magnetosphere has practical importance for modern technology. Satellites, power grids, and communication systems can all be affected by magnetic field variations and the influx of charged particles during magnetic storms. Understanding and predicting these effects requires detailed knowledge of both the Earth's internal magnetic field and its interaction with the solar wind. Future changes in the Earth's magnetic field will depend on the continued operation of the geodynamo, which in turn depends on the thermal evolution of the core and the ongoing crystallization of the inner core. Computer models predict that the geodynamo will continue operating for billions of years, ensuring that the magnetic field will continue to protect the Earth's atmosphere throughout the remaining lifetime of the Sun. The discovery and study of magnetic fields around other planets has revealed that the Earth's strong, stable magnetic field is relatively unusual in the solar system. Mars appears to have had a magnetic field in the past, but lost it billions of years ago, possibly contributing to the loss of its atmosphere. Venus, despite being similar in size to Earth, has no global magnetic field and has experienced significant atmospheric loss over geological time. These comparisons highlight the importance of the Earth's magnetic field for maintaining long-term habitability and suggest that the operation of a planetary dynamo may be a critical factor in determining whether a planet can support life over geological timescales. The Earth's magnetic field thus represents not just a fascinating geophysical phenomenon, but a fundamental requirement for the existence of complex life on our planet. The continuous motion within the Earth's interior creates a vast, interconnected system where processes in different layers influence each other across thousands of kilometers and millions of years. Heat flowing from the core affects convection patterns in the mantle, which in turn influences the movement of tectonic plates at the surface. The subduction of oceanic plates carries material from the surface back into the deep interior, where it may eventually affect the thermal structure of the core mantle boundary. This coupling between different parts of the Earth system operates over an enormous range of spatial and temporal scales. The crystallization of individual atoms of iron onto the inner core contributes to convection patterns that span thousands of kilometers in the outer core. The slow circulation of rock in the mantle connects processes occurring over millions of years, with sudden events like earthquakes that last only minutes. The magnetic field generated in the core influences the space environment around the Earth, affecting everything from satellite operations to the behavior of migrating animals. Understanding these connections requires studying the Earth as an integrated system, rather than focusing on individual processes in isolation. Modern geophysics increasingly emphasizes this holistic approach, using observations and models that span multiple disciplines to understand how the planet works as a whole. This systems perspective reveals the deep interconnections between processes that might seem unrelated when studied separately. The circulation of material between the surface and deep interior creates pathways for chemical exchange that operate over geological timescales. Elements that begin at the surface can eventually reach the deepest parts of the mantle through subduction and convection. Material from the core mantle boundary can return to the surface through mantle plumes and volcanism. These exchanges help maintain the chemical balance necessary for long-term planetary habitability. Water, carbon, and other volatile elements participate in these deep cycles, affecting everything from the composition of volcanic gases to the long-term evolution of the atmosphere and oceans. The rate at which these elements are exchanged between the surface and interior influences global climate over millions of years, helping to regulate surface temperatures and maintain conditions suitable for life. The Earth's internal dynamics also influence the distribution of continents and oceans over geological time. The patterns of mantle convection control where new oceanic crust forms and where old crust returns to the interior. The locations of volcanic hotspots, mountain ranges, and ocean basins all reflect the deep structure of mantle circulation patterns that have been operating for hundreds of millions of years. The slow drift of continents across the Earth's surface follows these deeper currents in the mantle. Africa and South America, now separated by thousands of kilometers of Atlantic Ocean, were once joined together as part of a single supercontinent. The mantle convection patterns that began pulling them apart over 100 million years ago continue today, slowly widening the Atlantic while gradually closing the Pacific. These continental movements occur so slowly that they are imperceptible within human lifetimes, yet they have profound effects on global climate and the evolution of life over geological timescales. The opening and closing of ocean basins affects the circulation of ocean currents, which in turn influences global temperature patterns. The collision of continents creates mountain ranges that affect atmospheric circulation and regional climate patterns. The positions of the continents also influence the global carbon cycle by affecting the rates of weathering and volcanic activity. When continents are clustered together in supercontinents, weathering rates tend to be lower and atmospheric carbon dioxide concentrations higher. When continents are dispersed, as they are today, weathering rates increase and atmospheric carbon dioxide levels decrease, helping to moderate global temperatures. These feedbacks between the solid Earth and the climate system operate over timescales of millions to hundreds of millions of years, much longer than the climate variations that occur due to changes in solar radiation or atmospheric composition. However, they play a crucial role in maintaining Earth's long-term habitability by preventing the climate from becoming too hot or too cold for extended periods. The study of past climate changes preserved in geological records reveals how these deep Earth processes have influenced surface conditions throughout the planet's history. Ice ages, periods of global warming, and mass extinction events all show correlations with major geological events such as the formation of supercontinents, large volcanic eruptions, or changes in the rate of seafloor spreading. Understanding these connections helps scientists predict how the Earth system might respond to future changes, including those caused by human activities. While human-induced climate change operates on much shorter timescales than geological processes, it occurs within the context of the larger Earth system that continues to evolve according to the deep processes we have explored together. The volcanic eruptions that occasionally remind us of the Earth's internal energy represent just the most visible manifestation of processes that operate continuously throughout the planet's interior. Most volcanic activity occurs along the boundaries between tectonic plates, where the motion of the plates creates pathways for magma to reach the surface. At mid-ocean ridges, the separation of tectonic plates allows hot mantle rock to rise toward the surface, where it partially melts to form new oceanic crust. This process occurs continuously along the 60,000 kilometers of mid-ocean ridge systems around the world, creating new seafloor at a rate of several centimeters per year. The heat released by this process warms the overlying ocean water and contributes to global ocean circulation patterns. At subduction zones, where oceanic plates descend into the mantle, the heat and water released by the subducting plate cause partial melting in the overlying mantle rock. This creates the magmas that feed the volcanic arcs found around the Pacific Ring of Fire and other subduction zones around the world. These volcanoes return material from the deep earth to the surface, completing part of the cycle that exchanges material between the interior and exterior of the planet. Volcanic hotspots like Hawaii and Iceland represent a different type of volcanism, fed by mantle plumes that rise from deep within the Earth's interior. These hotspots can remain active for tens of millions of years, creating chains of volcanoes as tectonic plates move over the stationary plume sources. The longevity of these hotspots provides evidence for the stability and persistence of deep mantle convection patterns. The gases released by volcanic eruptions provide a window into the composition of the Earth's interior and the processes operating at depth. Water vapor, carbon dioxide, sulfur dioxide, and other volcanic gases carry chemical signatures that reflect their origins in different parts of the mantle. The ratios of different isotopes in these gases can reveal whether the magma source has been influenced by subducted oceanic crust, continental material, or primitive mantle that has remained isolated from surface processes for billions of years. Volcanic eruptions also play an important role in the global carbon cycle, returning carbon dioxide from the deep Earth to the atmosphere. Over geological time, this volcanic carbon dioxide is balanced by the removal of carbon through weathering processes and the subduction of carbonate sediments, creating a long-term carbon cycle that helps regulate global climate. The study of volcanic processes provides one of the most direct ways to investigate the composition and behavior of the Earth's interior. Volcanic rocks preserve samples of mantle material that have been brought to the surface from depths of tens to hundreds of kilometers. The chemistry and mineralogy of these rocks provide clues about temperature, pressure, and composition conditions in their source regions. Earthquakes represent another manifestation of the continuous motion within the Earth's interior, though they occur much more suddenly than most geological processes. Most earthquakes are caused by the sudden release of stress that has been building up slowly as tectonic plates move past each other. The energy released in a large earthquake represents the accumulated effects of plate motion over periods of decades to centuries. The seismic waves generated by earthquakes provide our most important tool for studying the Earth's interior structure. These waves travel through the entire planet, changing speed and direction as they encounter different materials and conditions. By carefully analyzing the arrival times and characteristics of seismic waves from thousands of earthquakes, scientists can map the three-dimensional structure of the Earth's interior with remarkable precision. Deep earthquakes, which occur at depths of several hundred kilometers within subducting oceanic plates, provide direct evidence for the descent of cold, brittle rock into the hot mantle. These earthquakes occur because the descending plates remain cold and brittle for millions of years after they begin their journey into the Earth's interior, allowing them to fracture suddenly even under the extreme pressure conditions of the deep mantle. The global distribution of earthquakes clearly outlines the boundaries between tectonic plates, revealing the network of active geological processes that shape the Earth's surface. Earthquake activity is concentrated along mid-ocean ridges, subduction zones, and transform faults where plates slide past each other horizontally. The patterns of earthquake occurrence help scientists understand how stress accumulates and is released within the Earth's crust and upper mantle. Modern earthquake monitoring networks can detect ground motions smaller than the width of an atom, allowing scientists to study even very small earthquakes that provide detailed information about local geological structures. The continuous operation of these networks creates a real-time picture of the Earth's geological activity, revealing how the planet responds to the slow but persistent forces generated by mantle convection. The prediction of earthquake timing remains one of the most challenging problems in Earth science, primarily because the processes that control earthquake occurrence operate on multiple timescales and involve complex interactions between stress, rock strength, and fluid pressure. While scientists can identify regions where large earthquakes are likely to occur based on geological history and current stress patterns, predicting exactly when these events will happen remains beyond current capabilities. However, the study of earthquake processes has revealed much about the mechanical behavior of rocks under stress and the conditions that control when and how rock failure occurs. This understanding helps scientists assess earthquake hazards and design structures that can withstand the ground shaking produced by these sudden releases of geological energy. The gradual escape of heat from the Earth's interior follows pathways that connect the deepest parts of the planet with the cold vacuum of space. This heat flow drives all the geological processes we have explored together, from the circulation of liquid iron in the outer core to the movement of continents across the surface. Heat travels through the Earth primarily by conduction in the solid layers and by convection where materials can flow. In the crust and lithosphere, heat moves slowly by conduction through solid rock, taking millions of years to travel from depth to the surface. In the convecting parts of the mantle and in the liquid outer core, heat is transported much more efficiently by the motion of the material itself. The rate of heat flow varies significantly across the Earth's surface, reflecting the different geological processes operating in different regions. Heat flow is highest at mid-ocean ridges, where hot mantle rock rises close to the seafloor and new oceanic crust forms. Heat flow is lowest in the stable interiors of old continents, where thick layers of insulating continental crust reduce the rate at which heat can escape from the underlying mantle. Measurements of heat flow at thousands of locations around the world have revealed the global patterns of heat loss from the Earth's interior. The total heat flow from the planet's interior is approximately 44 trillion watts, an enormous amount of energy that dwarfs human energy consumption, but represents only a tiny fraction of the heat stored in the Earth's interior. This heat flow has been decreasing slowly over geological time as the Earth gradually cools, but computer models predict that it will remain sufficient to maintain geological activity for billions of years into the future. The slow rate of cooling ensures that the processes that make Earth habitable, including plate tectonics and magnetic field generation, will continue operating long after the Sun begins its evolution toward becoming a red giant star. The pathways by which heat escapes from the Earth's interior are intimately connected with the circulation patterns in the mantle and core. Hot mantle plumes carry heat directly from the core mantle boundary to the surface, creating volcanic hotspots and contributing to regional variations in heat flow. Cold, subducting plates carry heat downward into the mantle, creating thermal anomalies that can persist for hundreds of millions of years. The thermal structure of the Earth's interior reflects the balance between these different heat transport mechanisms and the distribution of heat sources throughout the planet. Computer models that solve the equations governing heat transport in the Earth's interior help scientists understand how this thermal structure has evolved over geological time and how it might change in the future. The study of heat flow also provides important constraints on the composition and structure of the Earth's interior. Different materials have different thermal properties, so measurements of how heat flows through different regions can reveal information about the composition of the underlying rocks. Variations in heat flow can also indicate the presence of fluid circulation, mineral phase transitions, or other processes that affect heat transport. The connection between the Earth's thermal evolution and its habitability highlights the importance of understanding these deep heat transfer processes. The rate at which heat escapes from the interior controls the vigor of mantle convection, which in turn affects the rate of carbon cycling between the solid Earth and the atmosphere. Changes in heat flow over geological time have influenced the composition of the atmosphere and oceans, helping to maintain conditions suitable for life throughout most of the planet's history. The remarkable stability of the Earth's thermal system over billions of years reflects the delicate balance between heat generation and heat loss that has been maintained throughout the planet's evolution. This balance has allowed the Earth to remain geologically active while avoiding the extremes of becoming either too hot, like Venus, or too cold, like Mars. Scientific investigation of the Earth's deep interior represents one of humanity's greatest intellectual achievements, requiring the development of sophisticated techniques to study regions that can never be directly observed. The methods that scientists use to peer into the Earth's hidden depths demonstrate the power of indirect observation and theoretical understanding to reveal the workings of complex natural systems. The global network of seismometers that monitors earthquake waves operates continuously, recording millions of measurements each year that gradually build increasingly detailed pictures of the Earth's internal structure. Modern seismic stations can detect ground motion caused by earthquakes on the opposite side of the planet, ocean waves breaking on distant shores, and even the slight bulging of the solid Earth caused by tidal forces from the Moon and Sun. Advanced data processing techniques allow scientists to extract information from this vast dataset that would have been impossible to obtain just a few decades ago. Seismic tomography, which creates three-dimensional images of the Earth's interior similar to medical CT scans, now provides detailed maps of temperature and composition variations throughout the mantle and core. These images reveal the locations of hot mantle plumes, cold subducting slabs, and the complex flow patterns that drive plate tectonics. Laboratory experiments that recreate the extreme conditions found in the Earth's interior have become increasingly sophisticated, now capable of subjecting tiny samples to pressures and temperatures equivalent to those found at any depth within the planet. Diamond anvil cells can generate pressures exceeding those at the center of the Earth, while laser heating can raise temperatures to several thousand degrees Celsius. These experiments reveal how familiar materials behave under conditions that are impossible to experience at the surface. Synchrotron X-ray facilities provide intense, focus beams of X-rays that can probe the atomic structure of materials under extreme conditions. These studies have discovered new mineral phases that exist only in the deep Earth and have revealed how the properties of common minerals change with pressure and temperature. The results of these experiments are essential for interpreting seismic observations and understanding the physical processes operating in the Earth's interior. Computer modeling plays an increasingly important role in integrating observations from many different sources into comprehensive pictures of how the Earth works. Modern supercomputers can solve the complex equations governing fluid motion, heat transfer, and electromagnetic field generation throughout the Earth's interior, predicting how these systems should behave under different conditions. The most sophisticated models now attempt to simulate the entire Earth system, including the interactions between the solid Earth, oceans, atmosphere, and even the space environment around the planet. These models help scientists understand how different parts of the Earth system influence each other and how the planet has evolved over geological time. Mineral physics provides the fundamental understanding of material properties needed to interpret geophysical observations. By studying how different minerals behave under high pressure and temperature, scientists can understand what seismic wave speeds tell us about the composition and temperature of the Earth's interior. These studies also reveal how materials flow and deform under the conditions found deep within the planet. The study of meteorites provides samples of materials similar to those found in the Earth's interior, particularly iron meteorites that represent fragments of the cores of ancient asteroids. These samples allow scientists to study the properties of iron-nickel alloys under laboratory conditions and to understand the processes that operate during planetary formation and differentiation. Paleomagnetic studies of ancient rocks preserve a record of the Earth's magnetic field behavior over millions of years, revealing how the geodynamo has operated throughout geological history. These studies have discovered that magnetic reversals are a normal part of the geodynamo process and have provided insights into the long-term stability of the Earth's magnetic field. The integration of all these different approaches creates a comprehensive picture of the Earth's interior that continues to evolve as new discoveries are made. Each technique provides a different perspective on the deep Earth, and it is only by combining these multiple viewpoints that scientists can understand the complex processes operating in the planet's hidden depths. Recent technological advances continue to push the boundaries of what can be studied about the Earth's interior. New seismic techniques can image smaller-scale structures with higher resolution. Advanced laboratory methods can recreate ever more extreme conditions. Faster computers can model increasingly complex processes. Each advance reveals new details about the remarkable system operating beneath our feet. The cumulative effect of centuries of scientific investigation has been to reveal the Earth not as a static, unchanging foundation, but as a dynamic, living system where matter and energy flow in patterns that connect the deepest interior with the surface where we live. This understanding transforms our perspective on the planet we inhabit, showing us that we live on a world that is alive with motion and energy in its deepest places. Future research will undoubtedly continue to reveal new surprises about the Earth's interior, as scientists develop new techniques and ask new questions about the processes operating in the deep Earth. The study of our planet's hidden depths remains one of the most active and exciting areas of scientific research, with new discoveries regularly challenging our understanding and revealing additional layers of complexity in the Earth system. The patient accumulation of knowledge about the Earth's interior over many generations of scientific investigation demonstrates the power of human curiosity and persistence to understand even the most inaccessible aspects of the natural world. Through careful observation, creative experimentation, and rigorous analysis, scientists have learned to read the Earth's hidden language and to understand the processes that operate in regions no human will ever see. This understanding has practical importance for predicting earthquakes and volcanic eruptions, for finding mineral and energy resources, and for understanding how the Earth system responds to environmental changes. But perhaps more importantly, it provides a profound appreciation for the remarkable planet we call home, revealing the deep processes that have maintained Earth as a habitable world for billions of years. As our journey together through the hidden layers of the Earth draws toward its close, we find ourselves with a transformed understanding of the ground beneath our feet. What began as a simple curiosity about what lies below has revealed a vast, interconnected system of extraordinary complexity and beauty, operating with patience and persistence that spans the entire history of our planet. The Earth we have discovered together is not the static, solid foundation it appears to be from the surface, but rather a dynamic, living world where solid rock flows like honey over millions of years, where liquid metal dances in patterns that create invisible shields extending far into space, where the very atoms that make up the deep interior continue their slow transformations, warming our world with energy that was stored billions of years ago in the hearts of dying stars. Every breath you take exists within the protective embrace of the magnetic field generated by these deep processes. Every step you make rests upon continents that drift slowly across the planet's surface, carried by currents of rock that move with the patience of geological time. Every moment of your life unfolds on a world where the deep interior maintains the delicate conditions necessary for the existence of liquid water, a stable atmosphere, and the complex chemistry that makes life possible. The processes we have explored together operate according to physical laws that have remained constant since the formation of the universe, yet they create an environment so stable and nurturing that life has been able to evolve and thrive for billions of years. The same convection currents that carry heat from the Earth's core today have been operating since before the first simple cells appeared in ancient oceans. The magnetic field that protects us now has been shielding the atmosphere since before complex life began its exploration of the land. This remarkable stability emerges from the dynamic balance between processes that operate on vastly different scales of space and time. The crystallization of individual iron atoms onto the inner core contributes to circulation patterns that span thousands of kilometers. The slow circulation of rock in the mantle connects events separated by hundreds of millions of years. Heat generated by the decay of individual atomic nuclei accumulates to drive geological processes that reshape entire continents. The Earth cradles all life in this gentle, persistent embrace of geological forces, maintaining the conditions that allow complex chemistry to flourish in the narrow zone between the planet's molten interior and the cold vacuum of space. The ground that feels so solid beneath your feet participates in circulation patterns that extend to the very center of the planet, connecting your resting place with processes that operate under conditions more extreme than anything found elsewhere in the solar system. In chambers of rock and metal that exist under pressures millions of times greater than atmospheric pressure, where temperatures exceed those found on the surface of distant stars, the Earth maintains the gentle processes that make this moment of quiet contemplation possible. The inner core grows imperceptibly larger with each passing day, releasing heat that drives the circulation of liquid iron above. The outer core flows in patterns of exquisite complexity, generating the invisible field that extends far beyond the atmosphere to protect everything within its reach. The mantle rises and falls in currents so vast and so slow that they encompass the entire history of complex life on Earth. Rock that is rising toward the surface today began its journey from the deep interior when the first animals were exploring ancient seas. The continents that provide the foundation for human civilization drift slowly across the planet's surface, following paths determined by convection patterns that have been operating since before the first sunrise illuminated this world. All of these processes work together in perfect harmony to maintain Earth as a stable, nurturing environment, a rare oasis of complexity and life in a universe where most worlds are cold, dead, and sterile. The deep Earth ensures that liquid water can exist at the surface, that the atmosphere remains bound to the planet, that the chemical cycles necessary for life continue to operate over geological time. Every natural law that governs the behavior of matter and energy in the Earth's interior contributes to maintaining the gentle world we call home. The study of these hidden processes reveals not just how the Earth works, but why it has been able to maintain conditions suitable for life for such an enormous span of time. The thermal engine that powers geological activity has been operating steadily for over 4 billion years, driven by energy sources that will continue to warm the planet's interior for billions of years into the future. The magnetic field that protects the atmosphere has been generated continuously throughout this entire period, providing an invisible shield that has never failed in its essential purpose. This deep time perspective shows that the Earth's interior represents one of the most stable and persistent systems in our solar system, maintaining the fundamental conditions for habitability despite dramatic changes in surface environments throughout geological history. Ice ages, periods of global warming, mass extinctions, and the rise and fall of countless species have all occurred within the context of this larger stability provided by the deep Earth. The patient operation of these geological processes over such vast spans of time creates a profound sense of continuity that connects us with the earliest days of our planet's history and extends far into its future. The heat flowing upward through the mantle today carries energy that was stored when the Earth first formed, from the collision of countless smaller bodies. The magnetic field protecting us now operates according to the same physical principles that have governed its generations since the core first began to differentiate from the surrounding rock. As you rest peacefully on the surface of this remarkable world, you are held gently by a planet that is itself suspended in the vast darkness of space, its internal fires burning steadily, its magnetic field extending like an invisible embrace that protects everything within its reach. The Earth spins slowly on its axis, carrying you through the cosmic night, while its deep interior continues the ancient work that has been maintaining conditions suitable for life, since long before the first living cell drew energy from its surroundings. The ground beneath you participates in geological processes that operate with a patience and persistence that transcends all human understanding, following patterns established in the earliest days of the planet's formation, and continuing into a future so distant it encompasses the birth and death of countless stars. The Earth holds you in its gentle gravitational embrace, while its deep currents of rock and metal work steadily to maintain the stable, nurturing environment that makes this moment of peaceful rest possible. As you settle into rest tonight, let the knowledge of these vast, patient processes bring you comfort and peace. Beneath the temporary concerns and rapid changes of daily life lies something enduring and reliable, a planetary system that has been quietly maintaining the foundations of existence for longer than life itself has existed on Earth. The ground beneath you is solid and dependable, not because it never moves, but because it moves according to rhythms so fundamental and persistent that they provide the ultimate stability. Every geological process we've explored together continues right now with the same gentle persistence it has shown for billions of years, ensuring that tomorrow will bring the same stable, nurturing world you rest upon tonight. The Earth breathes slowly, with the rhythm of deep time, its circulation patterns flowing with the patience of ages, its magnetic field pulsing softly with changes that unfold over centuries. This vast, quiet heartbeat of our planet continues as you sleep, as you dream, as you rest peacefully on the surface of a world that is alive with gentle motion in its deepest places. In the eternal darkness below, where no light has ever shone, the quiet heart of our world beats on, steady, reliable, and infinitely patient. The same processes that warmed the ancient seas where life first stirred continue their work tonight, maintaining the delicate balance that makes our world a home. Rest well, knowing that you are held safely by a planet whose deep interior keeps perfect time with the turning of the stars themselves.